This is part 8 of our Decision Trees series. Today's topic is feature importance in decision trees. In the last video, we implemented code to build a cart decision tree from scratch using recursion. In this video, we'll look at how to evaluate feature importance in decision trees. We will also look at how to determine the optimal tree depth using cross-validation. Now let's explore how to evaluate feature importance within a dataset. Our goal is to identify which specific features have the most significant impact on our model's predictions. You see, when building a model, it's not just about chasing high accuracy, it's about uncovering the why behind its predictions. Feature importance helps us do exactly that by assigning a numerical score to each feature, quantifying its contribution to the decision-making process. This allows us to see clearly which features are driving the results and which ones have little to no effect at all. Now let's dive into the mechanics of how decision trees actually calculate these important scores. We can easily calculate these scores using the information gain concept we covered in the previous video. Earlier, we explained information gain using the Gini index. Technically, though, information gain refers to entropy-based measures. When using the Gini index, the more accurate terms are Gini gain or Gini impurity reduction. For simplicity, we'll use the term information gain in a broader sense. To make this clear, let's walk through a simple, step-by-step example together. Let's take a look at this decision tree. It uses 3 key features: sex, p-class, and age. We'll see how each of these features contributes to the final prediction by calculating their individual importance. In this case, the sex feature appears once at the root node, while p-class and age are used 3 times each across the child nodes. The root node starts with 515 samples. Out of these, 307 belong to class 0, and 208 belong to class 1. To split this data, the CART algorithm has identified sex as the best feature, with a split point of 0.5. Based on this, 181 samples that meet this condition are sent to the left child node, while the remaining 334 samples are assigned to the right child node. Since sex is the very first feature used at the top of our tree, it's a clear indicator that this is the most important feature for our model's predictions. Now, let's calculate the information gain for each feature based on the Gini index. Before the split, the root node has a Gini index of 0.482. Once split, the left child node results in 0.344, while the right child node shows 0.321. By plugging these values into this formula, the information gain for the sex feature comes out to 0.153. Note that we weight each Gini index by the number of samples in that node. Next, let's calculate the information gain or Gini index reduction for the p-class feature used in this split. We have 181 samples before the split with a Gini index of 0.344. After the split, the samples are divided into 2 groups of 112 and 69. The Gini indices for these child nodes are 0.085 and 0.5, respectively. By taking the difference between the initial Gini index and the weighted average of these values, we find that the information gain for the split is 0.101. Repeating this process for other splits involving the P-class feature, we get an information gain of 0.158 in one case and 0.030 in another. To determine the overall importance of this feature, we take the weighted average across all its splits, which results in a final score of 0.061. Following the same logic, if we calculate the information gain for the age feature, it comes out to 0.032. Looking at the results, the information gain for sex feature is 0.153, followed by P-class at 0.061, and finally age at 0.032. Now let's normalize these values to see how they compare. These are the final importance scores for each feature. In summary, the sex is the primary feature, accounting for 62.2% of the total importance, while P-class and age follow at 24.8% and 13.0% respectively. Next, we'll build an optimal model to classify the Titanic dataset using scikit-learn's decision tree classifier. We'll also evaluate the feature importance to see which variables play the most critical role in our model's performance. First, let's load the Titanic dataset. To keep things simple, we're going to focus on just three features: P-class, sex, age. Next, we'll split the data into features and the target. Our features will include P-class, sex, age, while our target variable will be whether the passenger survived or not. Then we'll split the data into training, validation, and testing sets. Now, we'll experiment with different tree depths to see how they affect the model's performance, and then evaluate each model using the validation set. We use the validation set to choose the optimal tree depth and the test set to evaluate the model's final performance. We initialize the model with the current max depth D, fit the model to the training data, and measure accuracy on both the training set and the validation set. The accuracy on the training set is for reference only and is not used for model selection. The accuracy on the validation set is stored in a list for later use. After iterating over all possible tree depths, we identify the depth that achieves the highest validation accuracy. The tree depth corresponding to the highest accuracy in this list is the optimal depth. Next, we plot how accuracy changes across different tree depths. Next, we build the final model using the optimal tree depth we found and evaluate its performance on the test set. However, to make the tree easier to visualize, we set the maximum depth of the final model to 3. Next, we visualize the structure of the trained decision tree. Finally, we evaluate feature importance to understand how each feature influences the model. This attribute stores the feature importances that we computed manually earlier. Let's take a look at the results this code produces. When the tree depth was 1, the validation accuracy was 78.02%. As we increased the depth, the accuracy gradually improved. But after a certain point, it started to decrease slightly. The highest accuracy was achieved at tree depths of 3, 4, and 5. In this example, a tree depth of 3 was selected as the optimal value. Since the optimal depth can vary significantly with the validation set, this result should be treated as a guideline rather than a definitive rule. As the tree depth increases, the training accuracy increases, while the validation accuracy decreases. This indicates overfitting. Therefore, it is not recommended to make the tree too deep. The resulting tree looks like this. Sex is the most important feature, contributing 58.7% of the total importance, followed by P-class at 29.9%, and age at 11.4%. Now let's run this code. The results are as follows. So far, we have examined the feature importance of cart decision trees. In the next video, we will look at how to prune a cart tree using cost complexity pruning.